Okay, let's begin.
One of my friends is here, he's a professor that said that he doesn't sign, so I usually
December
get it
3
from
is
him.
mission 2.
Or
trying to understand like
December 16th.
my
How much
dad
is the
is
receipt?
great, so I
2020.
send him and you should receive it.
it's first half.
It's basically like integration and stuff. You go to the
Alright, let's continue. So, we're gonna pick up again with work. We're gonna learn how to compute work in several scenarios. Recall, probably the most basic definition that we will have for work is going to be, it is the integral of x dx, where f of x is a function that gives force exerted at point x over the interval a b. Want you to note here that our distance traveled is assumed to be in a straight line along an axis. When translated to functions. We can do this in general, not necessarily a straight line, not necessarily along the axis, but we need an object called a line integral, which you're going to learn about in multi-2. So we can't do that. So we're going to deal with very simple scenarios. We're pretty much finding the work done in moving objects into some, along some straight line path that we can visualize as being running along the x or the y axis. And that is the general definition for work. And it turns out that in the event that your function is a constant, this just turns out to force times distance. So if f of x is constant, say f of x equals k on AB, then this gives us that the work is going to be the integral from a to b of k dx, which is going to be k times b minus a, which this is just force times this is distance. So it covers, this definition covers an even more basic way that we think about work, force times distance traveled. We also spoke about units, so be very careful of that. Recall units and what they indicate. I'm not going to go over that again. So we're using pounds. There are many ways to interpret pounds, but we'll be interpreting it as force. Units and what they represent. So pounds, you see pounds, that's a force. You see grams or kilograms, that's a mass. Must multiply by gravity to get the force. Foot pounds or joules or Newton meters, these are units of work. Joules is also a unit of energy because work can be interpreted as a change in energy states, which is something again you learn about in multi-2, so I'm not going to dwell on it right now. those were the basics. However, applying it in different situations can be quite different, so let's actually look at that. Three situations that we know very well on how to apply this in the Calc 2 context. That's going to be in terms of springs with using something called Hooke's law. We are going to look at pulling problems. So how much work is exerted in pulling some weight, maybe up a building or along some path, some straight line path. We're also going to look at pumping problems. How much work does it take to pump fluid through some sort of tank or something like that? So these are the ones that you will be responsible for knowing how to set up and solve. So let's actually just jump into that. Hooke's law is the easiest one, so let's get that out of the way. This law is an empirical law. It says the following. The force needed to stretch or compress a spring without deforming it. So right, you're not stretching or compressing it to the point where it can't bounce back. Right, so as long as you're within the limits of not deforming the spring. But the force needed to do a stretch or a compression on a spring is proportional to the length the spring is stretched or compressed. Of course, we're looking at as beyond its natural length. So that's what the law says. Proportional just means it's going to be a constant times. The force is going to be a constant times the distance it's actually stretched. The constant of proportionality here will vary with the particular spring. So each spring will have its own constant of proportionality that will work based on the material that the spring is made up of and how thick the spring is, how long it is, that sort of thing. With the particular spring, and is called the spring constant. So in IE, Hooke's law says if we're looking for f of x, the force needs to stretch or compress a spring. It will be proportional to the distance that is actually been stretched. So this k here is the spring constant. This here x is distance stretched, compressed. Beyond natural length, that's very important. Oftentimes that's forgotten and that will lead to a lot of trouble. But this is the force needed, force required to stretch, compress spring x units beyond natural length. What do I mean beyond natural length? Let's make sure that we understand that. So, let's say we have a spring, it has length L, so this is representing the spring, which has length L. Now, what you can do is you can create a stretch on that spring. Let's say I can stretch it here, and let's say I stretch it an additional length A, and then I can stretch it again. An additional length B, and so if you're looking for the work needed to stretch it up to this point, is going to be equal to the integral from A to B f of x dx, where F is the force. Now, it's important that the A to B ignores the L length. It just matters that you're going from this length to that length. So you're always using the natural length of the spring as a reference point. This is where your 0 starts. So that's important. So you don't count the length of the spring itself. You only count the extra that you're stretching or compressing. So that's important. Let's do an example. So in your handout, we have a bunch of examples that we're going to do for the various situations. Problem 1, I think I only put one problem on input law. So, in summary, for springs, the work is equal to the integral of kx dx. It's always going to be like kx dx from A beyond natural length to B beyond natural length. It's always going to be that for itself. That's why this one is easy. So if you look at problem 1, a spring has length 15 inches and it takes a force of 750 pounds to compress the spring to 12 inches, so it's a very thick spring. Find the work needed to compress it an additional 3 inches. So that's the problem. So we have spring, length 15 inches, and we know the force to compress to 12 inches is 750 pounds. Find work to compress 3 additional inches. Okay, so here is how we would do it. We are going to set up this work equation. That's always going to be the equation for Hooke's law. Work is going to be the integral of kx. Not in general for springs. That's always going to be it because of Hooke's law. So what we can do is we know the work to move from A to B of kx dx applies specifically. Let's fill in some things here. What do we know so far?
F 12
Yeah.
is 750.
Come again?
I think F of 12 is 750 pounds. Is pounds in the force.
Okay, so we know that our f of x is of course kx, and we know that this is 750 pounds, right? So the fact that that 750 has units of pounds, it's telling us a force, right? So this is equal to k times, yes, you had a question?
No, I was gonna say, like, do you have to put the inches in feet? Like, so, like, 12 inches is 1 foot.
Oh, it depends on the units here. No, I think we can do like inch pounds or something like that. There's
Yeah,
nothing here.
It says
that
the
says-
answers in inch pounds.
Yeah, I gave an answer in inch pounds. I mean, if you do it in foot pounds, I would know how to get the equivalent answer. Right, so what do I put in for x? Well, it started at 15, I compressed it to 12, so how far beyond its natural length am I compressing it? Well, 3 units. So to compress it 3 units in length, I need 750 pounds. This in fact allows me to find k. So my k is going to be 750 over 3, which is going to be 250. So now I can actually plug that in. So what I have here is I know that the work is going to be the integral of 250x dx. How do I figure out the limits here?
Would it be 3 and 6? Because it was compressed 3 inches and then we're doing an additional 3.
Right, so it took us 750 pounds to compress it 3 inches. So we're starting from 3 inches beyond the natural length. And we want to compress it an additional 3 inches, so we're moving up to 6 inches beyond natural length. So the 15 itself and the 12 itself doesn't actually come into play here, because you're always thinking about the distance you are away from natural length. And so pretty much that's just you want to integrate this guy, 250 x dx. So very common errors will happen with students filling in the wrong limits, because they think that the numbers that are told are the numbers that they're using. You actually want to use the difference between the numbers that you're told. The difference in the natural length and what you want and where you are. So, I mean, this is compared to the integrals that we've been doing. So this is going to be 250 over 2 times x squared between 3 and 6. And this is going to be 250 over 2, 6 squared minus 250 over 2, 3 squared. And I think that all works out to the number, whatever number I put down there. 3375. And this is inch pounds. I did not convert anything, so. Questions on that? So you're talking about a spring, you automatically know force is going to equal to kx. You'll be given information to kind of figure out what your k is usually. But maybe you'll be given information to figure out something else. Just be careful with the limits on the integral. So you're looking at the difference between the natural length and the lengths you're given. But other than that, it's not really a big deal. That's going to be the theme with work. In general, the integrals we're going to get here, they aren't going to be very complicated to actually compute, especially compared to the integrals that we've been doing in the first part of the class in chapter 7. But setting them up is where the art lies. The art lies in setting them up. Not much more to hear about Hooke's law. Let's actually go to pooling problems. So, how do we lift and pull things? So, using the Riemann sums idea. So we know that work is going to be an integral. Sometimes we can just actually go back to the basics and look at how to actually build up that integral from the ground up. So usually what we'd want to do is we can usually slice up the object we're lifting, pulling into infinitesimal slices. We can find the work needed to move each slice, then sum these works via integration. So we're going to build up the integration formula for work by Riemann sums. Start slicing it up and you'll be able to actually do something. So normally we're going to want to be able to like set up some sort of coordinate system here. We usually set up a coordinate system to accomplish this. So I think the first problem here in your handout is going to be similar to one of the bonus problems on the test. Well, the first one is a little bit easier than the bonus problem on the test, but we're going to build up to one like the bonus problem on the test. Bonus problem on the test was more like problem 3. Problem 4 is even harder. So let's actually look at what we would do. So we have, so problem 2 on the handout. We have a 100-foot cable. It weighs 300 pounds. It hangs off the top of a tall building. Find the work needed to lift the cable to the top of the building. Okay? Seems me describing it in words, not that hard. So we have a very tall building. We have a cable hanging off this building. The cable is 100 feet. So this whole distance here is 100 feet. Now, we're going to use the Riemann sums idea. I'm not going to think of pulling this cable. I'm going to think of slicing this cable up in little pieces, figuring out what work it would take to move each individual slice. I'm going to add up these works with integration. So let's imagine that we have one of those particular slices here. Right, so I sliced it up. I am going to set my coordinate system thusly. I shall set x equals 0 to be at the base. Of course, the height is going to be x equals 100. I'm going to look at a slice that is a distance x from the bottom, which means that slice will have to be moved how far to get to the top? 100 minus x. So that's the distance that that slice has to travel. And now, let's say the slice here, its length is delta x. So I have my x-axis going vertically, slice it up into chunks, each one has width delta x. Imagine that it's at position x, it has to move a distance of 100 minus x to get to the top. Now let's actually figure out how much work it's going to take to move that shaded slice. So let's do work to move the slice. Well, that's going to be equal to force times distance. Right? Now what is going to be the force? This is where the units come in handy. You read the problem. If you want to figure out something about force, you're going to have to make sure you're getting the right units. What here tells us about force?
300 pounds.
300 pounds. That says pounds. That means that's a force. The entire cable weighs 300 pounds. Which means this slice weighs how do you figure out how much the slice weighs? Well, you have a 100-foot cable. The weight, 300 pounds. This means the weight per foot is 300 over 100 equals, it's 3 pounds per foot, right? Each foot of this cable weighs 3 pounds is another way you can look at that. So if I know each foot of this cable weighs 3 pounds, how many pounds does this slice weigh? Delta x feet of the cable.
3 times delta x.
3 times delta x. So 3 pounds per foot times delta x feet, the feet would cancel, you'd be left with pounds, which is a force. That slice weighs 3 delta x pounds. So that's the force that I'm working against. And what distance is it traveling? Well, we already figured that out. That was 100 minus x. This means the work to move this one slice is going to be 3 delta x times 100 minus x. Let's write this a little bit more suggestive. 3 times 100 minus x times delta x, putting it at the bottom. So now this means the total work is just going to be me adding up all these little works for all these little slices. And what you're going to realize is that actually looks like a Riemann sum, looks like f of x times delta x, and we're summing that over all the x's. So this gives us an integral of 3 times 100 minus x. The delta x becomes the dx when you throw it into the integral. And our limits, well, we want to move the entire cable, is that correct? Yeah, so we want to move all slices from position 0 to position 100. So this is going to be 0 to 100. That's going to be the work we need to do. The total work is going to be the integral from 0 to 100 of 3 times 100 minus x dx. And again, that's not going to be anything too crazy to integrate. Actually, just getting there was the harder part. It's going to be 100x minus x squared over 2 between 0 and 100, which is 3 times 100 times 100 minus times 100 times 100 over 2. $15,000. And we are in foot-pounds here. That's the work. Questions?
Should there be 100 on top of the unit sign? Or no?
Yeah, I mean,
Is it the same thing?
I just wrote it over, I want it to look like an infinite Riemann sum. So technically I want an infinite number of slices. So it would technically be, technically if you want to get too technical, it's going to be like I goes from 0 to infinity of, I'm doing it for each point. But the b minus a is built into the delta x component. So that'll be the 0 to 100. I think the next two problems actually just tweak this. And it actually makes it look a little bit more like the bonus problem on the test. So what if you had the same situation? And so now what's going to happen is there is like a huge bucket attached here. With a lot of water. This here now contains 500 pounds worth of water. So imagine that that's the situation. Let's just actually erase all this, even though we'll be doing a lot of similar stuff. So I think this was kind of like what the bonus in the test was like. So we had that cable hanging off a building, but it had a weight at the end of it, and the point was to pull the weight to the top of the building. How much work and hence fuel would this require? Well, here is how you would actually approach this one. You will think of the work total as the work to move the cable. You're going to add that to the work to move the bucket. You're going to add that to the work to move the water. And you're going to take the sum of the work. Now the problem says the bucket is of negligible weight, so we're told that this part we don't have to worry about, negligible. Made out of Iron Man's nanoparticles or something. So it doesn't weigh a lot, but it can hold 500 pounds of water. So, but we're going to ignore it. So here we have the work for the cable plus the work to move the 500 pounds of water. Now to actually move the cable, you're going to do basically what we did before. You're going to slice up the cable. You're going to say delta x feet of cable weigh 3 delta x and moves 100 minus x feet. So the work to move one slice of the cable is going to be 3 times 100 minus x times delta x, and the work total, work of the cable total, is going to be the integral of that from 0 to 100. Over here, How do we find the work to move the water? Well, the water is just a mass of 500. You can literally just use force times distance here. It is 500 pounds of force times it's moving 100 feet. So we are going to get 15,000 foot-pounds plus 50,000 foot-pounds. That is going to equal to 65,000 foot-pounds. So we had two objects to worry about here, the cable and the actual weight at the end. Normally when you have a situation like that, you just actually split them up, deal with each separately. So we already explained how to deal with the cable, and to deal with the water, it's just a mass of 500 that's being moved a distance of 100 feet, so you just do straight up work times distance. You could also technically, I mean, it's overkill here, but technically you could also do an integral from 0 to 100 of 500 because it's a constant force. It's always weighing 500 no matter at what point you are, and you'll still get that. You get 500x between 0 and 100. Fundamental theorem of calculus is going to give you that. So either way, you'll figure that out. Questions on that one? Slight variation on the last one. Let's do another variation.
Sir,
Yes.
you said that 500 is a constant force?
Yes.
But then, isn't the cable always the same force too?
No, because once you pull up the cable, the amount hanging off is less.
Oh, okay.
Right, so in the beginning there's 300 pounds hanging off, but by the time it pulls up half of it, there's only 150 pounds of cable hanging off. So the actual weight of the cable hanging off is changing.
Okay.
So that's why this one has to depend on x,
Oh, got it.
right? So when my x is 0, it's adding 300. But when my x hits 150, for example, when my x hits 50, for example, it's only adding 50, and so on and so forth. So that'll change, but the water itself isn't changing. So is 500. Problem 4. I think your textbook has a problem like this too. It's like, oh, there's a cable, and there's a bucket with water attached to the cable, and the bucket is leaking. It's like everything that could go wrong is going wrong in this problem. Okay, so problem 4 tweaks it even more. So we have that tall building. We are transporting water in a bucket, but the bucket is broken and it's dripping down. The water is leaking out of the bucket. The cable is pulled up at a constant rate. The water leaks out by the time it gets to the top. So we did all that work for nothing, essentially. Okay? So when the bucket gets to the top, no water is actually left. So we start out with 500 pounds of water. By the time we hit the top, there are only 0 pounds of water. Same 100-foot cable weighing 3 pounds per foot. What is the work in this situation? Now it's your turn. Take 10 minutes, try to figure that out. have a bucket, negligible weight. £500 at bottom, 0 pounds at top. Find the work done that, find the work done by lifting this bucket to the top. Give you guys some time to try that variation. Okay, let's see what we have here. So we still have this situation here. So we have the work for the cable. Let's just run through it again. So what we're going to do is going to imagine this cable where x is 0 down here, x is 100 up here. We're going to slice it into a lot of little slices and focus on moving one slice of length delta x, which is at a height of x and has to travel to a height of an additional height of 100 minus x. And so now I need the force times distance. I know that delta x feet of the cable weighs 3 delta x pounds. So the work for the slice is going to be force times distance. That's going to be 3 delta x times 100 minus x. And so here, the work for the cable is just going to be the integral of that, 0 to 100, 3 times 100 minus x at dx. And we did that already, that was 15,000 foot-pounds. The weight of the bucket, negligible. But if they had told us, oh, suppose the bucket weighs 20 pounds, then you would have just taken 20 times 100. That would be the weight to move the work to move the bucket. Now, if we look at separately the work to move the water, how are we going to do that? Well, do we have an idea? Yeah?
Is it 500 times 100 minus x delta x? Because at the bottom it would be the full force, and at the top would be 100 minus 100, which would be 0.
500 times 100 minus x. So you're saying your f of x for the water, is that what you're doing?
Yes.
Yes, well let's actually see how we could actually see that, which I think that actually works. So part of what I would do is here we're assuming leaking at constant rate. So what I can do is I can think about it like it's a straight line. Let's measure the force for the water in terms of the amount of pounds it's being exerted. When x equals 0, it's at 500. When x equals 100, it's at 0. So that's going to be a straight line, rise over run. So the equation of this line is going to be y equals mx, so it's minus 500, plus plus C, plus B is 5. Right, so around 500 divided by 100. Let's write it out. 500 divided by 100 plus 500 is the y-intercept. So it would actually be 500. So my f of x for the water would be 500 minus 500x, which is your 5.
Would it just be 5x?
5x, sorry. 5x, which is going to be 5 times 100 minus x. So, you had a similar idea. You needed a 5 here though, because now what happens is when your x equals 0, the weight is 500. And as it builds up to 100, your weight is actually going to be 0. So that would be the function. And so then I would just use the work equals the integral of force idea. So that is going to be the integral of from 0 to 100 of 5 times 100 minus x. That is going to be 5 times 100x minus x squared over 2. 2 is 0 and 100. That is going to be 5 times 100 times 100 over 2. So what is that, 25? Because this is going to go into that 50 times 25,000 foot-pounds. So, total work in this case is going to be 15,000 plus 25,000 foot-pounds. 40,000 foot-pounds here. That's the work needed. So looking at constant rate makes me think linear. So I just kind of set that up to be 500 at the beginning and to be 0 at the end. I could get an equation that deals with the actual force that is being exerted by the water in the bucket. And using work equals the integral of force idea, I get 25,000 added to the previous 15,000 gives me that. I think we'll stop there for now, because that we jump to pumping problems next, but by the time I explain that, we're not going to have time for an example. So we'll just pick up with that next time. In the handout, I do explain a little bit though about how to set it up, so you can try a problem or two, maybe try problems 5 and 6, more if you have time. Before I start, some homework on this.
So I wanted to just say you guys. Honestly, it's not bad.